Hey guys, this is chapter 7, and so let's get right to it. Okay, so chapter 7 has 4 sections. We're only going to talk about 3 of those sections here right now, and we'll get the 4th one coming into next week. Okay, so this is where we're going to actually talk about continuous distributions. And last week we talked about discrete distributions, which are where the values that a variable can take can be listed. So 1, 2, 3, 4, 5, the value on 2 dice, the value on 1 die, whatever. Continuous variables are a little bit different because they're the ones where you can take any value in the range. So if I said, what's the probability you roll a 1.5 on a dice? That would be weird, right? And you'd say the answer is 0, I guess. Or what's the probability you roll pi? And I guess the deal is that when we talk about this, we don't really think about the probability of an exact number, because if we're really thinking about continuous, then there's an infinite number of decimal places, which is kind of crazy to think of pi, right? Your favorite number, or e, or whatever. And the idea, if I say, what's the probability it's exactly pi? Well, the answer is going to be 0, because we're going to go to an infinite number of decimal places. So instead, what we tend to think about is this idea that it's really going to be between a couple of numbers. And so this idea that we're really going to think of this value right here, that the area of probability is going to be between 2 numbers. So you might say, well, gosh, how does that work? Well, it already sort of works, because when I say, what's the probability we roll a 3 on a die, that's really the probability of a number near 3. And so we could just round them all to 3. So if I say a 2.5 rounds to 3 and a 3.49 rounds to 3, then that works, and a 3.5 rounds up to 4, and you could say a 3.49999 whatever, right? And you can do it that way. So this idea that we're really going to be thinking now about sort of functions, and we're going to be thinking about ranges. Now, those of you who had calculus, you can imagine this idea that the probability of any exact number is going to be 0, because we're going to get those skinny rectangles. Those of you who haven't had calculus probably don't care about that. And so that's really where this idea comes from. Now, we can explain uniform range, treating it as a rectangle, and that certainly works. The book goes through it a little bit, and you have a homework question about that. But this idea that if we're going to say it's uniform between 2 and 12, so it's like rolling 2 dice, but instead of being that histogram shape that we had, it's going to be flat. Well, then you would say the probability is between 2 and 12 is going to be 100%, because it has to be between 2 and 12. And we couldn't say what's the probability it's exactly 10, but what's the probability it's less than or equal to 10. Okay, and we could do that, so on and so forth. Again, I'm not going to spend a lot of time talking about it. The book does a little bit more with that. But this idea that we're going to think of it as a rectangle going from 2 to 12. Yep. Okay, that was a better 12 than I thought. And then if we wanted to think about the probability it's less than or equal to 10, we would just make a slice off of the cake or the loaf of it like that. And so this idea that, here is 8 numbers worth, so that's 0.8 of the distribution, and then 0.2 is left over here, is how that could work. The middle value is going to work out just like you think. 2 plus 12 is 14, divided by 2 is 7, and that actually does work as we do that. I know it is sort of goofy. More important than the uniform distribution, though, is the normal distribution. And again, I'm using Dr. Shanshan Love's slides, but she uses 3 exclamation points to say that the normal distribution is the most important distribution. And I typically don't give anything 3 exclamation points, but she's exactly right. Most things that we measure that are interesting follow a normal distribution. So height, weight, body temperature, pregnancy, gestation rates, IQ, process variations when you're doing factory stuff, any of those kind of things, a return on your stock portfolio, any of those things is going to be normally distributed. However, the formula that describes it is nuts, right? And you can see right here, the formula, it has a pi and an e in it. You remember e to the x is one of those weird distributions. If we actually break it down into pieces, and again, I apologize sort of for my bad drawing, the idea that when we're near 0, then e to the minus 0 is going to be 1. That's a multiplication 1. So this number is going to cancel when we're near 0. And what we're left with is 1 over 2 pi. Well, that's actually a formula for a circle. So near 0, we have kind of half a circle. When we're not near 0, we have this e to the x thing. And we all know what e to the x looks like, right? It looks like an exponential shape. Well, it has a minus sign in front of it, so that means it looks like an exponential shape for negative numbers. And for positive numbers, it looks like the reverse of that. And boom, I just drew me a normal curve. You got to put a little duct tape here to get this to work, where it's sort of somewhere in between the two shapes. And of course, you can look in the textbook, or you can look on the examples in the my stat lab to get better drawings of the normal curve than that, if you think that's a good drawing of a normal curve, sorry. But that idea that this is actually too complicated a formula to use. And again, those of you who had calculus, especially if you had Calc 2, this is actually what we call an open form solution, meaning that you can't find an exact answer for it in many cases. So what we used to do was we used to have a table, and in fact, if you bought the paper copy of your textbook, in the back are these blue numbers that have a table where you can look up the values to give you the answer rather than calculating them in a real formula, which again is crazy. So we're not going to do that here, but we are going to sort of think about how we calculate it. Now, the mean and standard deviation are typically what we use to describe a normal distribution. So if you get a normal curve, a mean, and a standard deviation, we now know everything about it. We do call this a bell-shaped curve. And again, I'm drawing it here with my little drawing stick, which is weird. It does have these inflection points, which is where it switches shape. It is symmetric, despite how I drew it. And there you go. So here are some better normal curves. And you can see mean 0, standard deviation 1. We call this a standard normal sometimes. And it looks like that. But there's no particular reason it has to be that. We'll talk about how to transform it to make it that. We're going to use some algebra here next section. We can think about a mean -2 and a standard deviation of 2. Notice that's a fatter curve. Doesn't go quite as high. Here we have a standard deviation of 0.5. That's going to be a skinnier curve because the standard deviation is less. So that's how the normal distribution really works. And what we're going to be thinking about in terms of probability is that if we have a normal curve, the area under the curve is going to describe the probability. And again, those of you who had calculus will say, hey, that's an integral, and you'd be exactly right. And it's the integral of that crazy formula we had before. So if we want to say what's the probability that you're less than 1 standard deviation below the mean or more, we can just find the area under the curve and do that. And again, that's what that table in the back of the book does. We're going to, in practice, use either the spreadsheet or my stat lab to calculate the values, because again, the formula is just too nuts to actually calculate. And it's not like, oh, that's because this is the basic stats class. If you were in the one that had Calc 2, you would still use the table because again, it doesn't have a closed form answer. So as we think about how it works, if we say we know that cholesterol has a mean of 180 and a standard deviation of 36.2, we can draw a normal curve, and then we can think about, right, if you have a cholesterol higher than 200, it's considered to be high cholesterol, and your doctor will tell you to take some medicine or change your diet or do whatever. You'll have, you know, mine is 185, so I'm not quite there, but still enough that I worry a little bit about it. And we want to shade that region in the curve. And again, I'll show you the prettier one here a little bit later. There's the mean. The standard deviation is over here. That gives you 200. And that filled in is the value that it's going to work for it. So then if we can say that using that table or using the calculation, the area under that curve is 0.29, what does that mean? Okay, so that's what we're going to do. And so we draw the curve. 180 on the chart is the middle. The standard deviation is 36. Then we want to shade the area to the right of 200. And so again, I'm going to do it poorly here, and I'll show it to you pretty in the next one, then color that in. And it looks like that. Again, we can see it's going to be less than 50% because the curve doesn't get that far. And in fact, this idea that it's 29%. So the proportion of 20-something-year-old males that have high cholesterol is 29%. Or thinking of it backwards, the probability that a randomly selected one has high cholesterol is 29%. So in the next section, we're going to talk about doing more with that calculation. But that's really what's motivating us to do this, because it really is how we describe and how we explain things in the real world, because we know this normal distribution is everywhere and it lives inside so many of these real world phenomenon. All right, and the next chapter is come up here next. And where's my thing to stop the video? Oh, that's what it is. I have to clear the drawing first.